device. It's an alternative way to make power that doesn't use steam or turbines. It uses the fact that you can shape and scale the amount of energy that comes out of a flame as light, and tune the PV cells that can absorb that light and turn it into electricity. And so people always ask, how does this scale? Does it work well when it is really small? Does it work well when it's really big? And the crazy thing about it is it seems that the physics does scale across like all the way down from a single sodium atom to imaginable Dyson sphere around Sagittarius A, the super massive black hole in the center of our galaxy. So how does this work? So basically, I say that you can define a Dyson sphere as like you have a luminous object that has energy that is surrounded by hopefully an insulated set of solar cells or PV cells, that photovoltaic cells rather, that convert that light energy into useful electricity so you can do work. And you start with the atom. So this is actually a real-time Schrodinger evolved. Let me see if I can. Where's my cursor? There it is. All right. This is actually a real-time Schrodinger equation for the sodium atom. And it's basically, I'd never seen this. This was not available when I was a physics student. But it's running in the browser. It can work on your phone. All this stuff is going to be up on dysonsphere.fyi. Basically sodium and all the alkali atoms are special because they've got a full shell and the nucleus, and that's all tight together and doesn't interact much, full polycule. And then on the outside, you have an easily excited, I like to call it an in-cell electron, which can easily be knocked around. And it turns out they're rather single-minded, so they can very rapidly, they basically work as a dipole. The electron moves back and forth, and then the much heavier nucleus with all the cells has an opposite charge, and so it moves back and forth. And not only is it extremely strong, and so it emits this incredibly bright yellow light, yellow jacket, yellow light. This is this yellow sodium discharge. It also, they work together. So we think that this is actually pushing into what's extremely interesting for me. People are like, oh, a lot of quantum things require low temperature. So there were a bunch of Nobel Prizes won for Bose-Einstein condensates is extremely low temperature, which used this kind of atom, an alkali atom, and particularly sodium, in order to show that there's collective effects. And this is the same as two subwoofers that are in a building in phase with each other. They couple together and they output more power. And it's not quite lasing, but it's something called super radiance, super absorption and super transfer that ends up dominating the radiation. Anyway, it's getting a little complicated. Point being, the sodium atom is incredibly bright. If you calculate out just how much energy, once you've excited it, the rate of power that it can put out, it's extreme. Like you can end up with megawatts in a liter. But what happens is it doesn't just go straight out. It also absorbs, it has a high resonance. It's like a really, 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 imagine the best possible acoustic resonator that might have a Q factor of like 20. This has a Q factor of thousands and thousands. So it also absorbs. So the radiation is trapped. And so the question is, how does it scale? Does it scale in a way that is good? So starting from the sodium atom, we can scale to what we've done in the lab. So this is the world's highest temperature type heat exchanger, and we've developed it. It uses ceramic that is 3D printed in a kind of a photo resin that you make into this kind of compound arch shape. It's called a triply periodic minimal surface. And what that means is, because it has all this curvature, it's able to maintain the incredible temperature differences across, from here where it's air coming in less than 100 degrees to over here where the exhaust is coming out, where it's nearly 1400 degrees, the boiling point of salt. And salt is how we get the sodium in. So it's actually in a chemical loop. So it goes, salt first becomes more molten, and then it has a high surface tension and it wicks around all of the surfaces, including the tube, and including all of the different surfaces inside the heat exchanger. And that allows it to be continuously refreshed and act as a resonator while not being itself consumed. And the reason this works is because the sodium chloride has the strongest bond. It's the strongest bond energy because one's on the left side of the periodic table, one's on the right side of the periodic table. This one's an extreme incel. This one's extremely, well, the polycule needs another member and they connect. I They should teach chemistry this way. Anyway, so what that allows you to do is convert almost all of the energy into this single wavelength, almost a single wavelength. And what you get is, if you can compare it, so this is wavelength, and this is the amount of energy per, and this is a log chart. So almost all of the energy is showing up right here. It's actually this is actually measured from our system, and there are two kinds of silicon cells plotted here. This is the internal quantum efficiency of a silicon cell, and this is internal quantum efficiency of indium gallium phosphide, which is the highest efficiency cell to match that yellow. And as you can see, we're much closer. So the way that solar cells work is, it's called the photoelectric effect. Not the only thing Einstein won the Nobel Prize for, but sure. Oh, sorry. Okay, sure. Little closer. Hopefully some of the earlier can be fixed in post. So the amount of energy that light transfers comes in discrete packets, quantum mechanics, photons. If you have more energy than what's called the band gap of a PV cell, that extra energy is wasted. If you have less energy, then it can't absorb it at all. So ideally, you want your PV cells to have a band gap that is like just underneath the exhausted power, and that's here. So this is a much better light source than just a sun. So as we scale the system, however, we can actually change it. It's a little fiddly here. We can actually change it, and as hopefully this works. So is it changing? No, it's not. All right. Unfortunately, my Claude must have busted this immediately before. The fable was so great. Anyway, so all right. So what is, yeah, setback is, we have setback science by 1 week. What happens when you have an increasing amount of power is, because of this trapping, you get an increased amount of energy in the excited states. And those excited states can still leak out energy in different ways to other luminous lines. And one in particular, when you have two excited states and they collide, they can do what's called a pooling reaction, get one of them up to an even higher state, and then when that jumps down, that's a near infrared, which is right here. So what should it be happening when I'm scaling this is it will go up. Yeah, go up a lot. So, and it actually, the first thing that happens there is, well, yeah, first thing that, I don't know why it's fiddly, but actually it again, this is logarithmic, so there's quite a lot here. But then this a secondary can be added in which you can convert that excitation into even more infrared, and even better match for silicon. Why is this relevant? Silicon is like by far the cheapest source of energy in the world. It's just only available when the sun is around. So if you can tap into this with this light source, you can produce power continuously. So what are the kind of scales that we're talking about? Well, we can first start talking about, like, the first thing that we kind of want to make is something that can power a Starlink Mini and your Mac Mini and so on. But as you get larger and larger, it starts to get more and more interesting. So a friend of mine makes a private jet, says you need about a 1 megawatt to fly. A lot of people are like, hey, Danielle, how quickly can you produce 100 megawatts? Forgetting how much it will cost, because we desperately need it. Can it scale to that? And one thing I found very useful to convince Claude about this, because it would keep simplifying assumptions that was less extreme. It's like, well, one of the things that's the highest power that we ever run is like a rocket launch. So if you have a Starship super heavy launch or a static fire when it stays on the ground, the amount of power out is 330 gigawatts, which is an enormous amount of power. But if you've ever, I don't know if you've ever look next time there's a rocket launch, notice how it's yellow when it's on the ground, when it's close to the ground, and then it turns white. Why does it do that? The reason is the tiny amount of trace sodium that's just from the sea salt comes out and lights up the whole thing. You also saw the same thing when the Blue Origin rocket exploded. So what if you actually use this technique to make a system that can actually produce an enormous amount of power in a single installation? So if you calculate it out, the amount of total power that you're generating from that amount of fuel, which is like methane, liquid natural gas, and oxygen, which you can just condense from the air. That is, if you converted it, approximately the amount of energy, about 100 amount of power, about 100 gigawatts of power in a single installation, which is about the amount that is added to the electrical grid in the United States in a single year. So completely different kind of power plant. So extremely interesting. So what about building a Dyson sphere at an even greater scale? So there are kind of two branches here. One thing is for an earth shade. So one thing people talk about is as you increase the amount of power that goes to AI, even if it's green, it increases the amount of waste heat on Earth. Eventually we get cooked. What do we do? So one of the things that you can do is you can figure out, okay, how much anthropogenic global warming have we already cooked into this thing? And let's put a Dyson swarm, just, for good weather, put it in L1, which is the Lagrange point in between Earth and the sun. And it at 0.01% of a shade, like a planet shade, that will cancel out all the global warming. It's also 200 terawatts of incoming power, and on the order, near to 100 terawatts of power, right? So that's a very interesting thing for AI, especially if you can start producing the solar panels on the moon, because the moon regolith itself contains silicon, it contains all kinds of oxides, and so you can make solar cells. It's also dramatically easier to get something into lunar orbital velocity, and then once it's in lunar orbital velocity, it can slowly maneuver to wherever it needs to be with light and electronic transport.
Hey, sorry.
Sorry.
I know this is a small room and it seems like a microphone
Isn't
a whole lot,
no.
but it's crucial to just speak into it. It's just pretty directly, just so it's
Sorry, I'll try to have it locked here, but maybe there should be a compressor somewhere. Okay. All right, great. So if you have an earth shade, then basically up to the design point of it is providing the amount of cooling that we want. This is a great place to get energy, and it could be substantially cheaper than even Earth-born energy if you can generate the satellites and send them, and basically you can spin launch or railgun launch to lunar orbital velocity and use almost no energy compared to launching something from the Earth's surface. So I think it's good for alignment if AI eventually gets power off of Earth, because then we don't get cooked by the waste heat. In addition to the fact, we're burning a lot of fuel. But then it was once you get to really large scale. So you basically, you have heavy industry near Mercury, you start to disassemble it, and you can send stuff out, into the ecliptic. There's so much extra power in the sun. You can actually change the direction that the energy is going. You can have the sun has an enormous magnetic field, and it's moving through the Milky Way. And so it's actually accreting gas, and it's an exhausting gas and photons at the same time. So if you change where the light is going out, and you change where the exhaust is going out, and you change where stuff is coming in, this is basically a Bussard ramjet, which is this idea where you actually make, yes, I see in the audience, you make a fusion reactor that absorbs the interstellar gas and moves around. So what can you do with this? Well, I'm not saying it's an easy thing to do, but this is an awesome way to make a generation ship. Over eons, the sun can scoot around throughout the Milky Way, visit other stars, and potentially find another star that can scoot around even more, which means that you can get to the final prize, which is if you have energy, if you have at the center of the Milky Way a supermassive black hole, the amount of extractable energy when you drop something into the accretion disk, it's about 50% of the rest mass energy, which is enormous, which is like about 50 times the amount that you would get out if you fused everything. Okay. And the amount of power that's available if you were to do that is of the order of 10 to the 33 watts, which is like just so dramatically. I had a big argument with Eliezer Yudkowsky last night, much respect. Is like, they can use you for energy, they can use you for mass. And it's like, well, there's like 10 to the very large number of more energy and mass out there in space. It's a big place. And we don't necessarily have to set things up for resource conflict. We can use ideas to get out of it. So let me see if I can show a few other things that didn't quite make it into this flow. Just 1 second. And then we can probably discuss, well, yeah, sure. Yeah. Sorry? Dyson sphere.fyi, which I hope is up right now. Let's see if Claude managed it. Yeah. Unfortunately, this part isn't working, so I have to fix that from my Cloudflare settings. But yes, it will be up, and the intent is, so I discovered one of the things that people always ask is, why didn't anybody ever why didn't anybody think of this before? And there's usually a lot of reasons. I mean, this is pretty esoteric. You need to know at least a few things, sort of, how sodium lights work or fireworks work, how PV cells work, and light divides into different wavelengths. And you need to decide to build it, which involves high temperature flames and designing. That's all right. And you need to do all these different things. But I was like, why isn't there any study of this? Like there were 20 different ways to do thermophotovoltaics, and nobody decided to try adding sodium when this is known, like this is demonstrated in high school physics class, just flame tests. And these are the most efficient lights in the world. These high pressure sodium lights are the most efficient lights in the world. Let me just move back here to where we at. Yeah, so this is a one-dimensional simulation of how much energy gets out into each wavelength. So as you see it, as you increase the amount of this is in WASM. If you tell your AI to use WASM, everything gets incredibly fast. Okay, so as you increase this, you get more and more of this self-trapped line, and then you get more and more energy coming out in this 819, this near infrared. Yes. Sorry. All right. So this is the amount of pressure of the primary sodium, and you can have a secondary sodium that basically traps it like an annulus of additional resonant material that's just trying to trap it. And this will be up as well. What I was trying to get to is there is a code at Lawrence Livermore that does radiative transport. And the reason you can't have it is because it's used for H-bombs. But I'm not going to use it for that. So I'm making my own. uh, and it's going to go up on our website and up here, and it just isn't integrated yet. Another thing to say is that there's sort of two really important questions in terms of the actual physics of how this works. One is the emission actually coupled like a laser or like this the so-called super radiance? If you click it on or off, it can change a lot, but apparently not with these parameters. All right, maybe it's off. Hold on. Yeah. No, it's not working. Okay. Formerly, super radiance would make some difference, some degradation. Additionally, the amount of energy and the amount of irreversibility that happens when you combust something, when you do a chemical reaction, um, as you get to higher and higher temperatures and you drive it towards a steady state where that temperature is so high that the reaction products also thermodynamically they thermalize and split apart, and so the heat itself is keeping things apart. When things are that hot, the amount of energy that is available to the system as you when you react more, it doesn't create any entropy. It's reversible, and the available bond energy, we think, is probably significantly excited beyond what would be the kinetic temperature. So the kinetic temperature is the temperature of all of the molecules and atoms moving around, and you calculate that. But when a reaction first occurs, the energy is in excited states on the molecule, and it can excite this light emission. And we think that because of this, we can get much, much higher emission densities than we previously had, which is exciting for the highly tuned cells that we have, because you can match the yellow much more exactly. And it's exciting because it means that there's more amount of energy that's in the yellow light anyway and trapped, and that's what creates the near infrared light that matches silicon and gallium arsenide so well. Yeah. So I have been kind of blowing through it. Maybe I can get some questions from the audience. Sure. Yes. Yeah, that's pretty much it. Sorry. Sorry. Um, to understand carefully, uh, it is we use the energy in heat to excite sodium, which produces yellow light, which can be converted efficiently. So, yes.
So, you did a transition from chemical systems to solar
Yeah.
point, and I wasn't clear on what it was that you want to do with sodium past the chemical.
Yeah, it's a good question. So the traditional Dyson sphere is you surround the sun, but different suns are different colors. And actually, every astrophysical or a whole pile of astrophysical objects that we know actually have a corona that is bright in the sodium lines. That is, it's low density, but it's bright. And the temperature, if you measure it, is like 10 million degrees. The sun is like this. It's not quite 10 million degrees in the optical for Earth, but it is like that. Because stars are different colors, your optimization is going to be different for each different astrophysical object. Blue, red giant star, but you can convert the energy using a kind of secondary. So one can imagine for the sun that you actually don't exactly know best way to do this, but get more sodium into the layers of the sun, and it will emit light in that band. But probably for the sun, it doesn't make a huge amount of sense to like engineer the whole thing to be emitting specifically. At the extreme end, when you have a small star, you can add or like the Sagittarius, like if you have an accretion disk or something, if you have sodium in the accretion disk, when it's a moderate temperature, it will emit incredibly brightly in the yellow. And then you can absorb. Yes.
Yeah.
Yeah.
So could you like to have two layers, one which is just a block of like it goes blocks of sodium that re-radiate, or that would that be less more ionized?
It could be. So there's long been ideas of like they call it a matryoshka Dyson sphere, where you have multiple layers, and the one of them radiates out and you cover the other. But if depending on where you put the atoms, you can pump more of the energy and use it and then recycle the rest. So if you had a cavity that was like a very good mirror, um, and then you pick out only this part of the spectrum, then that's a way to do what we're doing. But astrophysically, it's difficult. I mean, most of the time when you're doing a Dyson sphere, you really are going to want to have a swarm. You're not going to have a complete cavity. The energy is going to go back into the sun. But it is. But if you have a partial cavity, and you like let light out or let exhaust products out in one direction, you can do all sorts of things, including like I said, scooting around the local neighborhood.
Ja, så att du kör my lines for the first. I had a motor key take the first like
Right. So we're trying to make over the next couple of years both small scale devices that are your general purpose utility, provides power, heat, light, water, just condenses the chemically created water at small scale. And we think that this will be, a general purpose sidearm. Everyone's going to want it. At large scale, there's a huge demand for data center power. And so we are trying to find hundreds of megawatts or gigawatts of basically natural gas, and also at a place where you can generate a lot of hydrogen from excess solar. And so you can switch between natural gas and hydrogen, and hopefully mostly hydrogen, at that much larger scale, as we increase the amount of empirical data behind, if you scale this, can you get higher and higher efficiencies out with silicon cells, and that could happen pretty fast, but maybe 2 years from go, when there's a whole pile of money. And then I think, and people kept asking me, hey, Danielle, why is Elon talking about a mass driver on the moon? This is why. I don't know when he's intending to do that, but it could happen quite quickly. Blue Origin has actually made solar cells from lunar regolith. And, you don't even need to throw it very fast to get into lunar orbit, although you need to do a little correction. Matt, what?
so in this power generation generated way, I would wire over 850 that. And how does this stack up against the boats it's CERN? So energy recover.
Yeah, so we think that we can fairly beat what's called a simple cycle gas turbine, which is sort of 30% efficiency. So we think 30% plus. But we think that if you optimize everything, you can probably get to 60% or so when everything is working in your favor. And you can also do what's called a combined cycle plant, which combines it with spinning things and boiling water. Maybe boiling alcohol off of the back of the solar cells will generate power. And you need a certain amount of air flowing through, so you can imagine having a turbine on the back end. And so this is how the highest efficiency fuel systems have achieved a combined cycle and a steam plant over 60% efficiency. We think we can get over 70% long term.
You really have much need to stop through your data. How long?
Good question. So, at least hours. So it's a very good. This is one of the most caustic environments imaginable, right? You have sodium chloride, which is also and extremely high temperatures. How are we hundreds of temperatures higher than, MIT, national labs, all that? Well, the main thing is we're using ceramic. So chemically, aluminum 2, oxygen 3 is really difficult to react to anything else. It's in such a ground state, basically. So it tolerates the salt in it. In fact, the salt makes it stronger. It fills in all the pores and it distributes strain. The second thing is we have to use these. Let me show you. So not this. Not this. Okay, so sorry. So this shape, these kind of corrugations solves the critical structural problem. So even though the thermal expansion coefficient of the ceramic isn't very high compared with steel, it's maybe 1/3, it's much, much harder. It's actually like 9 on the Mohs scale. It's like within a factor of 4 of diamond. So on one hand, the thermal stresses become really great if everything holds together. But on the other hand, if you have just a little bit of strain relief, then you can dissipate almost all of that stress. It's like the inverse of the problem. So the key is you have to make it curved in all of the different dimensions. And there's a mathematical shape called a triply periodic minimal surface. This one here is called a Schwartz diamond that divides the space into 2 different volumes. And so that's the perfect sort of building block for a heat exchanger, but also for all of the structure. So that's what we do. And it's similar to how does a gas turbine or how does a rocket nozzle survive, even though the gas inside is much, much, much hotter than the melting point even. You do regenerative cooling. So the amount of air that's coming in equals the amount of air that's going out, plus the fuel. So it's cooling on the way in plus radiator. Yes, it's both. And you need both. But there's a fair amount of variation you can have. Yeah.
Is there a nuclear reactor design now about sodium in this?
I love this question. So many nuclear reactors already use sodium as heat pipes. But it's a relatively lower temperature. It gets to vaporized at about 600 degrees. But many people have asked me, hey, is there any way to do this with nuclear? And there's a bunch of interesting ones. The main thing is because it's heat that is being recycled, and it gets very bright that way, then you can use this technique to both spectrally shape and also make sure that everything inside a chamber is about the same temperature. Same way that heat pipes do, except instead of heat pipes going out to another heat engine, it's light going out a window. Now, the thing is, you have to redesign your nuclear reactor completely. I mean, this works non-linearly. Many people know that as the temperature increases, the power increases is T to the 4th for black bodies. Well, it's even faster here. It's even faster. It's almost to the 10th power at these regimes. So what you would need is a nuclear fuel that is a ceramic that can tolerate the sodium, tolerate the salt, and can tolerate the high temperature. So there is such a thing. And actually, the very best refractory oxides in the universe is thorium oxide. Which is, in addition to being a great nuclear fuel because it is breathable, you'll burn the uranium in place. First, it captures the neutron, becomes uranium, and then it burns the uranium. So when both of those things happen, you can solve proliferation, I think. Although, there's still some other edge cases. Like if you have a neutron fluence, you can do stuff with that. But you can design a system that is an amplifier. This is my favorite, where you start with a seed fusion. The fusion doesn't generate much power versus how much you put out, but it does generate neutrons. The neutrons multiply in the nuke, and you get about 16 times the energy out per fission, and you get 1 over 1 minus k for multiplication. So you can get like 2,000 times as much energy out per fusion, which means that you can run fusion at much lower than Q, and so you can have a tiny little thing. You can imagine, having a completely nuclear powered propulsion system that you never need to refuel, basically. And that's very interesting. Yeah. um,
Let's say I'm a killer and I need I go out briefly step through like what the your Ross air this
yeah. So we think that we'll be able to get in a modular system about 10 megawatts, maybe more, in a shipping container. We might need to be more competitive in this because Boom Supersonic is saying 42 megawatts, although no one has ever demonstrated that within an order of magnitude. So but those could just be stacked up. At the larger scale, where you're doing kind of a monolithic thing, like the super heavy going into a salt bowl surrounded by a tower of like an giant cathedral tower of silicon cells, where they're designed to handle not just 1 sun of intensity, but maybe up to 20 suns of intensity. It's like pretty big skyscraper type thing, but a single installation could equal the amount of electricity capacity added to the electrical grid in the United States in one installation. So, but it's still a mega structure. It's like hundreds of meters tall, like, and very large and very bright. But it's not like we haven't built those. I mean, literally the Starship Super Heavy, 330 gigawatts of fuel rate. And so we could probably convert, a third of that up to a half of that. Well, because it's so super linear, yeah, I mean, you can see it. Oh, what temperature is necessary to see the night yellow light? So you can see it if you've got salt around on just like any open flame, like natural gas flame or whatever. You can already see it. I've seen, but it's super linear. It's like really, really, really to a high degree. And so as you increase the temperatures, so for us, the design point is you want the flame plasma to be at least at the boiling temperature of salt, which is 1400 degrees C. And then ideally you actually drive it so that the chemical reaction is held near 3000 degrees C. Yeah. With preheated air or oxygen and fuel. Yes? It's a good question. We should talk after. There are a lot of things that you definitely want in a nuclear reactor. One is passive stability. So, not liquid, but actually super critical. So if you have a moderator that is deuterium oxide and sodium chloride, and super critical, then that works great. We can talk about. Yeah.
When you scale up, it's all a event, all the so does much bigger column, or you put more and more column.
Yeah, I mean, at some point, it's the practical fabrication limit. That's the limit at the time. One scale I like to think about is, those backyard. I think there's a bunch of backyard heaters with a quartz tube. Those quartz tubes are mass produced. They're so cheap. They're like $40. One of those things could probably handle about 100 kilowatts. So that is sort of the modular scale size, where if you have 100 of those, 10 by 10 in a shipping container, that's 10 megawatts. And that's pretty interesting. As you get larger and larger, you have to start doing construction that is tile-based. This is the same thing with fusion reactors. See, you have to do something different. And instead of using a glass containment, you'll actually use the air itself. If you have, I mean, you instead of having the wall be right up against this extremely high temperature thing, we have like a swirling column of air inside the tube, and that keeps it off of the wall because it's heavier because it's colder. So, but you still need to get the energy out somehow. So there's got to be. So it's probably not ideal to do an open system. You probably want a cavity, and we've experimented with basically quartz, which is great, but eventually gets corroded by the salt. Sapphire, which is great, but it can crack, and you're terrified about it because it can build up stress. And amorphous alumina, which is pressed together in something called hipping, which makes all the grains stick together and it makes it translucent. But we don't use that as much for experiment because we can't see through the thing. So, but that's what everybody uses for high pressure sodium lamps, which have like 75% radiative efficiency, although not all of it is in light that you can see. Looks like we got room for one more question. I think you were going to ask something. No. Nobody else? All right. Yes.
Wasn't like underrated.
Ha ha. You need special juice. One thing is that we kind of call it, fundraising by stunts. We do all these kind of engineering things, and whatever scientific information we can gather, but also we try to show as many people as possible with their own eyes. I didn't bring it this year, but last year we had a big light cell operating in one of the gardens. It lit up the whole thing. So that's one thing. I had previously raised a bunch of money for my previous company, Lightcell Energy, which was compressed air energy storage. And so I had some reputation from that. So that made it easier. It didn't make it easy. And we're still fundraising. So, it would probably be easier if I used all the AI stuff that I'm doing and be like, we're just an AI company. However, I insist that since it's energy to AI, and this is the relevant durable constraint, and that we're using the AI to understand how to actually enact our company, how to build everything, and it's a huge intuition pump for like pushing the AI to the limits. And we're sitting in San Francisco, that these things reinforce each other, and so that's how we keep raising money.